So the first reaction we're going to talk about is addition. Now, that's going to happen if your tetrahedral intermediate, once your nucleophile attacks, does not have any good leaving groups on it. If neither R nor Y are good leaving groups, then you will end up with an addition product. So addition could proceed through one of three basic mechanisms. First, you could have protonation of the oxygen, and that gives you an activated complex that the nucleophile can then attack. Or you could have nucleophilic attack and formation of that alkoxide, followed by a second step of protonation. Or you could have both of these things happening in a concerted fashion. So this is kind of like the E1 versus E2 versus E1 CB mechanisms for elimination. Now, I want to point out in this section that metal cations and other Lewis acids promote nucleophilic attack. So, for example, when you have lithium aluminum hydride getting added to a carbonyl, that lithium cation is going to be pulling some of this electron density off of the non-bonding electrons on the oxygen, and that is going to put a bigger delta positive on your carbon. Also, boron trifluoride is often explicitly added to reactions as a Lewis acid catalyst. So remember, boron trifluoride would not have a full octet, so it would be electron deficient, and so it would attract, as boron compounds do. It's going to attract the electron density of the oxygen. So the last topic to cover for Chapter 7 is the addition of enols and enolates to carbonyls. So I'm just going to sketch the overall reaction. You have a base that's going to deprotonate an alpha carbon, and we're going to end up with this guy, and he is resonance stabilized, like so. And this is your nucleophile for an aldol reaction, and it is called an enolate. So then we're going to attack a second molecule of that same ketone or aldehyde. And now this enolate nucleophile is going to attack the carbonyl carbon. So we end up, I'm going to try to draw this stacked on top of each other, showing where everything gets connected. So here's the new bond, and here's where it connects into your second molecule of, in this case, 2-butanone. And so I've drawn in red what the new carbon-carbon bond is. And this would be after protonation at the oxygen. And so this is what we would call an aldol addition. These things can be acid or base catalyzed, and they are reversible reactions. And so an aldol addition is either an acid or a base catalyzed dimerization, two of the same unit coming together and bonding to each other, dimerization of ketones or aldehydes. Now, an aldol condensation, which is what we did in lab last year or 2 years ago, is where we lose, if there's a hydrogen left on this carbon, then that hydrogen and this OH group eliminate and give you a new double bond where the red new single bond is. And so we get this product as a final product. And that would be an aldol condensation product. So normally for ketones, the aldol addition product is not favored, but the condensation part, where you dehydrate and you lose water, thermodynamically can drive that reaction all the way to the aldol condensation product. And the reason is the formation of this conjugated system here, which is, energetically favorable. So aldol additions and condensations are very important because you're forming a new carbon-carbon bond under very mild conditions. So some typical conditions are listed in Scheme 7.3 on page 684. And if you remember from the aldol condensation that we did in lab last year, that was at room temperature with 10% sodium hydroxide, 10 mole percent or so. So pretty mild conditions for forming carbon-carbon bonds. One particular variant of the aldol condensation is something called a Claisen-Schmidt condensation. And so this would be a crossed aldol condensation. So the last reaction that we did was a self-aldol condensation, but if you had two different carbonyl compounds, one for your nucleophile and one for your electrophile, then you're doing a crossed aldol condensation. And so you want to be able to choose which of your carbonyl compounds is going to be the nucleophile and which one is going to be the electrophile. Otherwise, they both might be deprotonated, and depending on whether molecule 1 or molecule 2 is the nucleophile, you can end up with a variety of products. So we are always aiming for selectivity in our chemical reactivity. And so if you remember from lab, I'm sure we all remember from 212 lab, these were our two reactants. So I want you to think for a minute about why we had those reactants. First of all, which one could be the nucleophile? You have to have a carbon next door to the carbonyl carbon, so alpha to the carbonyl, that has a proton on it, an sp3 hybridized proton. And so if we look at benzaldehyde on the left, on one side of the carbonyl is a hydrogen, on the other side is a carbon that has no hydrogens on it. So there's nowhere that molecule can be deprotonated. Whereas indenone, the compound on the right, to the left of that carbonyl is the aromatic ring. There's no proton there that you could deprotonate. To the right is one carbon that has the necessary protons on it. And so those are the only protons that a base in this system would be able to deprotonate. That for as weak of a base as you can get, those are the most acidic protons in this whole mixture of both compounds. And so if the base deprotonates there, then we have formed the indenone carbanion resonance stabilized, like so. Okay. And so the carbanion form of this intermediate is the active nucleophile, and so it is going to attack benzaldehyde. When we add some dilute aqueous acid, that alkoxide tetrahedral intermediate is going to protonate. This is where we would have the tetrahedral intermediate form. And So we have bonded to that carbon in the indenone. And that carbon has hydrogen left on it. And so these guys eliminate and give you a new double bond here. And so you'll see that we do in fact form a little conjugated system. There's your conjugated system. And that was your, except I think one of them had a methoxy group on it. That was basically your aldol condensation product. But you didn't know that you were doing a crossed aldol condensation, and that specifically when you have aryl aldehydes like this that have to be the electrophiles, that is called a Claisen-Schmidt reaction. So there you go. So if you're wanting to do an aldol condensation, but both of these structures that you need have potential hydrogens on them that could be deprotonated, so your electrophile has two different kinds of protons on them at the alpha positions, your nucleophile has one kind. So if you wanted to end up with this product up here at the top, you would basically need to do something to ensure that you selectively form the nucleophile out of acetone. And so what you can do is you can first react what you want to be your nucleophile with a stoichiometric amount of lithium. And we're talking lithium metal. So remember, lithium metal is pretty reactive. It's kind of dangerous to handle. But if you react a stoichiometric amount of that with your desired nucleophile piece, then you can form this basically organolithium reagent as your nucleophile. And then as a second step, add the electrophile that you want it to go for. Now, I do want to mention the stereoselectivity of this reaction when you form your enolate stoichiometrically beforehand. If you form an E-enolate, and this section up here talks about how to form one enolate versus the other, don't worry about it, but if you form an E-enolate, you get an anti-addition product. If you form a Z-enolate, you get a syn-addition product. So let's see if we can break that down. E means trans, and so the enolate is this piece here, and it is E right now because the oxygen on one side is trans to the more important functional group, the R prime on the left side. The double bond would be right here for that enolate. The Z enolate, let's see if we can see it in this structure. That would be the Z enolate, and the oxygen is on the same side of this double bond as the R group on the other side. So that is a cis-like, and it would be Z. And so the lithium is still complexed to the enolate, and it begins to complex with the oxygen of the electrophile as well in the transition state. And so if your electrophile has a bigger R group on it, it's going to want to be in the equatorial position. Here's your electrophile in each of these reactions. So you notice that in both of those drawings, the R group is in the equatorial position where it has the most space. And so then you go through the bond formation, and once all the correct bonds are broken and formed, you end up with these resulting syn and anti products. So I think that about does it for Chapter 7 for us. Thanks for listening.